In this video, I'm going to be focusing on Bohr's model and the whole idea of this line spectra, emission and absorption line spectra. And so the first thing I want to kind of do is just kind of go through and show the special features about Bohr's model. And so first thing you have to understand about Bohr's model is that this was only done with hydrogen. The main reason for that is, as you should know by now, hydrogen only has one electron, meaning the fact that there is only an attraction between the nucleus and that one electron, and there's nothing else kind of involved in that whole entire atom. And so the problem kind of comes whenever you start adding more electrons, but we'll talk about that in later on chapters. So the first thing I want to kind of discuss is about actually how this thing is set up. And so this big sphere, or the dot in the center, is going to be representing your nucleus. The first circle around this is going to be your n equals 1. And all n equals 1 really means is that you are close to the nucleus. And if you kind of go out one more ring from n equals 1 to n equals 2, now you're kind of talking about the second, again, energy state, or in this situation, that is the first energy state that you can have, that you would have as an excited state. And then you keep progressing further and further out. You go n equals 1, n equals 2, n equals 3, and you can go on so on and so forth to about n equals 7. And so we kind of go through and start looking at these. All that n really means is the smaller value of n means that your electron is closer to the nucleus. The larger the value of n, the farther your electron is from the nucleus. And so when we talk about ground states, this is where the electron resides without any influence, without any energy put into the system, without anything else kind of going on. So the ground state is the lowest state that your electron exists when it is completely unactivated, unexcited, anything else. And so whenever you do somehow excite your electron by maybe shining some bright light on it, or in this situation we kind of go from here, you can shine some light, in this case HV, or H nu, sorry. H nu just represents energy, and so I'm saying I'm just shining some light or energy onto this electron, and this electron gets what we refer to as excited and moves up to an excited state. And so whenever energy is absorbed, you are going to go from a lower energy state up to a higher energy state. And so think about this concept as going upstairs. And so if you have to go up the stairs, you need to provide your foot with enough energy to go completely up those stairs. You cannot stop anywhere in between. And so this idea is what they refer to as quantums. And so all quantum means is that you have to reside on one of these steps. You have to reside or exist either on this step or this ring or this one or this one. You cannot exist anywhere in between. And so quantum just means that you have to have a whole number value to establish where you're actually residing. Or in this case, your n equals 1 is your ground state. Your n equals 3 is going to be your excited state. Please note, I am not saying anything about it n equals 2.75 because, again, that cannot exist. It just doesn't happen that way. And so one thing that Bohr kind of mentioned is, or I guess kind of implied with his model, is that these atoms do not exhibit energy whenever they are in their ground state. And so these electrons, they're still spinning around, they're still moving around, but you do not have any change in energy. You do not have this atom releasing any energy until there is actual change in wherever these electrons reside. And so in that instance, he's just saying that you can only change these electrons' energy whenever you actually have a transition in these electrons. And so if we go back and take a look at this one right here, whenever you have just your ground state, no energy is being released from this atom right now, meaning the fact no light is coming from this atom right now. And so the only time that these things are going to release or absorb energy or even change their energy is if they are hit with a photon that has enough energy to go or to transition this electron from one step to the other. And so in these instances, again, nothing happens until this energy is supplied into this atom. This electron is going to go from a ground state to an excited state. But as soon as it's on that excited state, one thing you have to understand is potential energy is going to be greater than what it was down here. And so as we've kind of mentioned in the past, potential energy needs to be minimum. That's just how Mother Nature loves it. Potential energy will always go in the route that it can in order to become less than what it was to begin with. And so here, as soon as this atom is up there, as soon as the electron is up there and excited, it doesn't want to be up there. It wants to go back home. It wants to be where it was nice and comfortable and no energy issues. And so the only way it can do that is if it releases the same amount of energy that it took to go up there, if it releases the same amount of energy back into the environment, like light or energy or heat, it's going to go from a higher energy level down to a lower energy level. This is what we refer to as emission. Absorption is going from the lower up to the higher. Emission is going from higher energy level down to a lower energy level. And so when we kind of go through and start talking about this, as I've kind of covered here, the only time you're going to have energy released is whenever you have, again, these transitions between these two levels. So the next video I'm going to post is about Rydberg's equation, and that's the whole idea of figure out if you're talking about this N or that E, all of them can be correlated to each other. But before I move on to that, I want to kind of go over and discuss this whole idea. What the heck does Bohr's model and these weird looking lines have to do with each other? And so when we kind of start talking about this concept of energy levels and transitions, one thing that I need you to know and memorize, and again, it's on this slide at least twice, is what I'm talking about here whenever I say N1 equals 1 for ultraviolet series, your N1 equals 2 for visible series, and your N1 equals 3 for infrared series. And all I mean by that is your N1, or the transition that you're going to be going from and to and everything, is always going to be 3. Meaning the fact that if you have any transitions going from 6 to 3 or 5 to 3 or 4 to 3, those are going to be in the infrared region. And the same kind of deal applies with your visible. If you have any transition going from 6 or 5 or 4 or 3 all the way down to 2, those are going to release energy that falls into that visible range. The UV range is if you have anything going from 6 or 5 or 4 or 3 or 2 all the way down to 1. And so the reason why this happens, and again, why this has to be a 3 and a 2 and a 1 in these circumstances, is because remember, all of these energies are associated with wavelengths and frequencies. And so the bigger the distance that you're going to be traveling, it's going to have an influence over the amount of energy that's going to be released. And as energy is related to wavelengths, each one of these kind of falls into that specific range that was on that table, the electromagnetic spectrum table. And so each of these, again, is going to release energy or release a wavelength that falls into the UV range. These are all going to give you like a wavelength between 450 and 700. And these are all going to give you the infrared range. And so one other thing I need to point out here is if you look at this table right here, diagram, if you look at this little diagram here, we're talking about hydrogen atoms. And so one thing you should hopefully be completely comfortable with is the fact that hydrogen atoms only have one electron. And when we're talking about a sample of hydrogen atoms, we're talking about a lot of hydrogens that all have one electron. And so each one of those electrons in each one of those hydrogens is going to be making a different transition. So that's why even though we only have one electron, in the visible spectrum, we can actually see 1, 2, 3, 4 lines. That just means that some of the electrons in the different hydrogens are making a transition from a N equals 5 to an N equals 2, which again corresponds to a big energy or a small wavelength of this purple color of 410.1. This other transition going from your N equals 5 to your N equals 2 is again going to be a smaller transition or less energy, so it's going to be a bigger wavelength of 434.1. And then this lighter blue color, again, this transition from your N equals 3 to N equals N equals 4 to N equals 2 is again going to be represented by a wavelength of 486.1. And this little tiny red guy right there is going from your N equals 3 to N equals 2, represents the 656.3 nanometers. And so if we were to again kind of talk about the UV range, please notice on this UV emission spectra, you have 1, 2, 3, 4, 5 lines. 1, 2, they're all kind of clumped up there. There's 3 right there, 4, 5, because you have 5 different transitions of these electrons that will go, or that will produce different wavelengths. And so, last thing I kind of want to point out is the difference between emission spectra and absorption spectra. And so emission spectra, as I mentioned, is what's pictured here when we have a higher electron going from a higher energy level down to a lower energy level. When this happens, this electron is going to be releasing its energy out into the environment. And as far as we're concerned about right now, it's going to be in the form of light. And so the emission spectra will be this black band with a few colored lines in between. Whereas the absorption spectra is going to be the opposite of that. And so the absorption spectra is going to happen whenever you have energy coming into the electron to make it excited. This electron is going to absorb the energy, go from a lower energy level to a higher energy level. So if you look at the absorption spectra of hydrogen, it will basically, with a little bit of inconsistencies here and there, but it'll be pretty much the exact opposite of this, where you'd see the entire rainbow of the spectra missing this purple, this blue, this indigo, and then that red. And so you can kind of think about these as like a one-way street. And so the emission spectra shows you where all these wavelengths can again be emitted, where the exit side or exit door is for these electrons at 410, 434, 486, and 656. Whereas the absorption spectra is saying you can enter in any of these regions all right here, but these 4 spots are reserved for electrons exiting and exiting only. And so if you take a look, Google it, I'm sure you can find it. But the absorption spectra of hydrogen will basically be the opposite. And again, you'd see the whole entire visible spectra, the rainbow, missing these spots or having the black bars there instead of these colored